Hello friends, myself Nalnikant Jana. Our today's topic is time average values of kinetic energy and potential energy in SHM. What is time average value? So before going to the time average value, we should discuss a little bit. In our previous class, we have already discussed about the kinetic energy in SHM, the potential energy in SHM, and also the total energy, which is the sum of kinetic energy and potential energy in SHM. Let us write the expressions what we have obtained in our previous class for kinetic energy, potential energy and the total energy of a body in SHM. We have already found out kinetic energy is equal to T is equal to half m omega square into root over of a square minus y square, and potential energy is equal to V is equal to m omega square y square. So, total energy is equal to sum of kinetic energy and potential energy, which is half m omega square a square. Sorry, here is one. Kinetic energy T is equal to half m omega square root over of a square minus y square. Potential energy is equal to V equal to half m omega square y square, and total energy is equal to T plus V equal to half m omega square a square. Today's discussion is about the time average values of kinetic energy and potential energy in SHM. Then what is time average value? If Q is a function of T and is a quantity, and we have to find out the time average value of this quantity Q, then we can write Q average value is equal to 1 by T integration Qt dt. This is the expression for the time average value of any quantity Q in the range of 0 to T. This is the general expression for the time average value of any quantity. But our aim is to find out the time average values of kinetic energy and potential energy of a body executing SHM. So, in the similar manner, we can write the time average value for kinetic energy as time average value of kinetic energy is equal to T average, which is equal to 1 by T integration over the range 0 to T half m v square dt. But we have already found out the kinetic energy of a body in SHM is this much. So, here we can replace that value and this equation becomes as 1 by T integration 0 to T half m omega square root over of a square minus y square. Now, we can put this in the form like this omega square into root over of a square minus y square can also be replaced in terms of sine and cosine as 1 by T integration 0 to T half m omega square into a square cos square omega t. A square cos square omega t, and here is the dt, here is the dt. Now, we have to perform the integration. Since half m omega square s square are constant quantities, so we can put them outside and the integration will be for cos square omega t only. Okay, t average will be equal to 1 by 2 t m omega square s square within integration 0 to t cos square omega t dt. But to integrate cos square omega t, we have to take the help of 1 plus cos 2 omega t. So, we can write this as m omega square a square divided by 2t, and within integration it can be written as 1 plus cos 2 omega t whole into dt. Now, by expanding this we can write m omega square a square by 2t. So, this is 1 plus cos 2 omega t by 2. So, this 2 can be taken outside and this can be written as m omega square a square by 4t, and within integration it will be from 0 to t 1 plus cos 2 omega t dt, which is equal to m omega square a square by 4t, within bracket it will be integration from 0 to t dt plus integration from 0 to t cos 2 omega t dt. But we know that the integration of sine and cosine function within a period of t will be equal to 0. So, this term vanishes and hence this expression will become as like this. Now, integrating dt over the period 0 to t, we can get it will be t from 0 to t and hence it is t minus 0. Now, I can write here m omega square a square by 4t, within bracket it will be t minus 0. Hence, the time average value of kinetic energy now becomes as m omega square a square by 4. This is the expression for the time average value of the kinetic energy of a body executing SHM, where m is the mass of the body, omega is the angular velocity of the body, a is the amplitude of oscillation. But previously we know that the total energy of the body executing in SHM is E is equal to half m omega square a square. So, we can write this as, but E is equal to half m omega square a square. So, this T average will be expressed as half into half of m omega square a square, which is equal to half of E, that is the time average value of kinetic energy of a body executing in SHM is equal to half of its total energy, half of its total energy. Now, we have to find out the time average value of potential energy of the body executing in SHM. What we have done here in calculating the time average value of kinetic energy for potential energy, we have to follow this similar method. So, in deriving the expression for the time average value of a potential energy, now let us write what is time average value of potential energy. T average is equal to 1 by 4 m omega square square, which is equal to half of E. Now, we have to find out the time average value of potential energy of a body executing in SHM in the similar manner as we have done in case of time average value of kinetic energy. Okay, let us write the time average value of potential energy is equal to V average, which is equal to 1 by T integration from 0 to T V dt. But we have already found that the expression for V is half m omega square y square. So, here we can write 1 by T integration 0 to T, in place of V we can write half m omega square y square, which can be expressed as integration 0 to T half m omega square. But we know that in case of SHM, y is nothing but a sin omega t. So, here we can write as a square sin square omega t dt. Now, half m omega square a square all are constants. So, they can be put outside the integration, and hence this becomes as m omega square a square by 2t. Within integration, it is from 0 to t sin square omega t dt. Now, this sin square omega t dt can be integrated in terms of cos function, and we have to convert this sin square omega t into 1 minus cos 2 omega t by 2. So, this expression will be rewritten as in terms of cosine function as. So, this expression can be rewritten in terms of cosine function as m omega square a square by 2t within bracket, and within integration it will be written as 1 minus cos 2 omega t into dt divided by 2. Now, these 2 can be taken outside. So, this expression becomes as m omega square a square by 4t, and within bracket we can expand these two terms as integration from 0 to t dt minus integration 0 to t cos 2 omega t dt. But already we have shown that the integration of sine or cosine function over a period of t vanishes. That means this factor becomes 0. So, this expression reduces to this much only. Now, this function reduces to this much. Now, we have to integrate the dt, and the integration of dt will be t over the period of t will be written as m omega square a square by 4t, and within bracket it will be t minus 0, which is equal to m omega square a square by 4, that is the average value of time average value of a potential energy is also equal to 1 by 4 m omega square a square, which is the same as the time average value of kinetic energy, which is previously shown that it is also half of the total energy. Hence, the time average value of a potential energy is also same as the time average value of kinetic energy and is also equal to half of the total energy. Here we have finished the time average value of kinetic energy and the time average value of a potential energy, and also shown that both are same and are equal to half of the total energy. And if we add up these two quantities, that means T average plus V average will be equal to how much? 1 by 4 m omega square a square plus 1 by 4 m omega square a square, which will be equal to half of m omega square a square and is equal to the total energy of the body executing in SHM. That is, what will be our conclusion? From the time average values of kinetic energy and potential energy, we found that the sum of the time average values of kinetic energy and potential energy is equal to the total energy of the body executing in SHM. Generally, this type of question often asked us, derive the expressions for the time average values of kinetic energy and potential energy of a body executing in SHM. Otherwise, these questions will be asked us so that the time average values of kinetic energy and potential energy are same and are equal to half of the total energy of the body in SHM. Otherwise, also this question may be asked as so that the sum of the time average values of kinetic energy and potential energy of a body executing in SHM is equal to the total energy of the body. Okay? I hope you should have a better understanding regarding this time average values of kinetic energy and potential energy. Now, we will switch over to the damped harmonic oscillation. So, now our topic is damped harmonic oscillation. Okay. Now, we will discuss about damped oscillations or damped vibrations. Generally, the questions are asked like this: what are damped harmonic oscillations? Derive the differential equation for damped harmonic oscillations, obtain its solution, and also discuss the cases of overdamping, critical damping and underdamping. These damped vibrations can be asked in these manners. First of all, we have to know what are damped harmonic oscillations. Then we have to find out the differential equation for damped harmonic oscillation, and similarly we have to find out the solution of this differential equation, and from the solution we have to discuss the different probable cases like the case of overdamping, critical damping and underdamping. Okay. Before going to the details of damped harmonic oscillations, let us first know what is the meaning of damping. Damping means destroy or decrease. Damped vibrations means the vibrations whose energy decreases gradually and also the amplitude decreases. So, we can define damped vibrations as the oscillations whose energy decreases and amplitude decreases with time. With the passage of time, its energy decreases and also the amplitude decreases, and graphically we can show a damped harmonic oscillation like this. This is the graphical representation of the damped harmonic oscillation whose amplitude gradually decreases with time. If here we take t and here is the displacement, then its amplitude gradually decreases, and if we plot the graph for its energy with time, then its energy also decreases. But simultaneously you may ask that if the energy or amplitude will not decrease in oscillation, then what type of oscillation it will be? It will be another type of oscillation which is known as undamped oscillation or free oscillation. So, we can now consider that when the amplitude and energy of oscillation remains constant, that type of oscillation is known as free oscillation or undamped oscillations. If the amplitude and energy of oscillation decreases with time, then this type of oscillation will be known as damped harmonic oscillations. The examples of undamped oscillations are the particles vibrating in electromagnetic waves, a particle vibrating in free space, their motions will be under undamped oscillations. But if a body executes its oscillation in a resistive medium, then its amplitude and energy will decrease with time and its oscillation becomes damped. What is a resistive medium? The medium which offers opposition, that is force to the motion, then it decreases the amplitude and energy, and due to this opposing force an undamped oscillation becomes damped. So, our air medium is an example of a resistive medium. If a body will oscillate in a resistive medium like our air, then with time its amplitude and energy will gradually decrease. For example, if a small child is in a swing and if we give an initial effort to the swing, then the swing will oscillate. but after certain time the swing starts decreasing its oscillation and simultaneously ultimately it will come to rest. If you will ask, we have given an initial effort, the swing started oscillation, but why the swing came to rest? Because the swing is in our air medium, which is a resistive medium, which offers opposition to the oscillation of the swing. That is why after some time its amplitude and energy decreased to 0, so that the swing stopped oscillation. Now question arises, if our air medium is an opposing medium or resistive medium, then any body which will be in oscillation in this medium, its oscillation will be damped and it cannot be undamped. Now question arises, if a body oscillates in our air medium, then its oscillation is definitely damped, and we have to find out what should be the equation of such type of damped oscillation. And if the equation is like a differential equation, then what will be its solution? So we have to find out now the differential equation of damped oscillation and also its solution. Let us discuss all these things one by one, and I have already clarified what are damped harmonic oscillations. Once again I am repeating, what are damped harmonic oscillations? These are the oscillations whose amplitude and energy gradually decrease with time. Where these oscillations are found? The oscillations of any body in a resistive medium is always damped. The example of resistive medium is our air medium. So any body oscillating in air medium possesses damped oscillation. Okay? Now we have to find out the expression for the differential equation of damped oscillation. Let us start deriving the differential equation for damped oscillation. Undamped oscillations become damped oscillations only when the body executes its oscillation in a resistive medium. Resistive medium means the medium which offers opposition to the motion. Now, if we consider the oscillation of a body in a resistive medium, it will face two types of opposing forces, and these opposing forces or resistive forces are due to the restoring force and also due to the resistive force of the medium. But the restoring force is due to the SHM of the body, and from defining the SHM we have known that in SHM F proportional to minus y and F is equal to minus ky, where k is the force constant. Here I am writing F proportional to minus y implies F equal to minus s y, where s is the proportionality constant and is known as the stiffness of the body, which is the force per unit displacement, that is s is equal to minus f by y. So this stiffness is the force per unit displacement, and the second force which opposes the motion is the resistive force, which depends directly on the velocity of oscillation. That means the opposing force due to the resistive medium opposes directly to the velocity. That means the second opposing force is the resistive force which varies directly with the velocity. That means F proportional to minus dy by dt, where y represents displacement and dy by dt represents velocity and the negative sign represents opposition. Now, this can be equalized to F is equal to minus r dy by dt, where r represents the proportionality constant and is also equal to the force per unit velocity. Force per unit velocity. Now, in discussing damped vibrations, we have come across two resistive forces. One is the restoring force, which is F equal to minus Sy, and the second one is the resistive force due to the medium, which is equal to F equal to minus R dy by dt. And these two opposing forces oppose the motion of SHM of undamped oscillation and make that oscillation damped. So, to discuss the motion of damped oscillation, we have to take into account these two resistive forces for the motion of oscillation. But from Newton's law, we know that a body executes its motion only when it is acted upon by a force, and according to him, this force will be equal to mass into acceleration, and you must have known that F equal to ma, and a is the acceleration which is equal to the double derivative of displacement, that is your F will be m d square y by dt square. Now, this force causes motion, these two forces offer opposition. So, we can write m d square y by dt square must be equal to minus sy minus r dy by dt, and taking all these quantities to one side, we can write m d square y by dt square minus r dy by dt plus r dy by dt plus sy will be equal to 0. Dividing all these factors by m, we can write d square y by dt square plus r by m dy by dt plus sy equal to s by m into y equal to 0. Now, let us put this r by m as 2k and this s by m as omega square. So, this equation will be written as d square y by dt square plus 2k dy by dt plus omega square y equal to 0. This is the differential equation of damped vibrations, where k is equal to r by 2m and omega is equal to root over of s by m. Now, we arrived at the differential equation of damped oscillation. The third question arises, if this is the differential equation, then what will be its solution? So, let us proceed to find out the solution of equation of damped vibrations. Exactly in the previous case what we have done in our previous classes, in solving the differential equation of SHM, first we have chosen a solution like y is equal to a sin omega t. Then by taking their derivatives time and again, we arrived at the given differential equation. That is why what we have chose is the correct solution of differential equation of SHM. Today, exactly in the similar fashion, we will choose one solution of this differential equation, and then we have to justify that what we have taken is the correct solution of this differential equation. Let us proceed to find the solution of this differential equation of damped vibration. Okay, solution of damped oscillation. Let us choose the solution as y is equal to a e to the power alpha t. Let us choose the solution of the differential equation of damped oscillation as y is equal to a e to the power alpha t. Now, taking the derivative of this equation, we can write dy by dt will be equal to a e to the power alpha t into alpha, which is equal to a alpha e to the power alpha t, implies dy by dt will be equal to alpha a e to the power alpha t will be termed as y. Similarly, taking the derivative of dy by dt, we can write d square y by dt square, which will be equal to alpha into alpha y, which is equal to alpha square y. Now, putting all these values of y, dy by dt and d square by dt square in our differential equation of damped oscillation, we can write the equation as, in place of d square by dt square, we can write alpha square y plus 2k. In place of dy by dt, we can write alpha y plus omega square y equal to 0. Now, taking y as common, we can write alpha square plus 2k alpha plus omega square whole into y is equal to 0. Now, we have taken that the displacement of y cannot be 0. Hence, this equation will be true only when the bracketed term vanishes. That is, now alpha square plus 2k alpha plus omega square will be equal to 0. Because y is not equal to 0 and this equation is 0, ultimately this will become 0. And this is a known equation of quadratic equation, whose solution can be obtained from the general formula which must have known from your previous classes, that if x square plus 3x plus y, sorry, x square plus 2x plus 5 equal to 0 is a quadratic equation, then we can find its solution from a general formula which is known as your x equal to minus b plus minus root over of b square minus 4ac whole divided by 2a. This is the general formula to find the solution of a quadratic equation. Here, this equation is a quadratic equation whose solution will be alpha, and hence using this we can write a is the coefficient of this alpha square, b is the coefficient of alpha, and c is the coefficient of omega square. Hence, we can write alpha equal to minus 2k plus minus root over of b square will be 4k square minus 4ac, 4 a is 1 and c is omega square, 4 omega square whole divided by 2a, a is 1. Now, here we can take 4 as common, and taking the 4 outside the root over, it will become 2, and this becomes as minus 2k plus or minus 2 into root over of k square minus omega square whole divided by 2. 2 gets cancelled. So, this alpha becomes as minus k plus or minus root over of k square minus omega square. Now, we found that alpha is this much, and putting the value of alpha in the equation where we have taken y is equal to a e to the power alpha t, then we can write the general solution of this differential equation as the general solution of this differential equation now becomes as y is equal to a e to the power minus k plus root over of k square minus omega square into t plus b e to the power minus k minus root over of k square minus omega square into t. This is the solution of this differential equation of damped oscillation, where we have put alpha as minus k plus minus root over of k square minus omega square. Now, this solution will become simpler if we will find the values of a and b, where we have taken a and b as constant quantities. Okay, to find the solution of or find the values of a and b, let us proceed as follows. Let us apply the boundary conditions to find out the values of a and b. What are the boundary conditions? If a body is at rest and is hanged from a roof, and we have to execute SHM on this body, then what we have to do? We have to keep the body one side and then release it. One side means we have to take that body to the extreme position, and at the extreme position, if we release, then the body will execute SHM. Now, if we apply the boundary condition, then at the extreme position at t is equal to 0, then y is equal to y0. where y is the displacement and y0 is the maximum displacement, which we have written previously as capital A. Here I am writing y0 because here A is already taken as a constant, that is why in place of amplitude I am writing y0. So, from the boundary condition we know that from the boundary conditions we know that if we put the body to the extreme positions, then the first boundary condition is at t is equal to 0, y equal to y0, where y0 represents the maximum displacement or amplitude. Again, at t is equal to 0, that means at the extreme positions we have already shown that the velocity of the body executing SHM is 0, and for velocity we have written it as v is equal to dy by dt. That means at t is equal to 0 at the extreme positions, this dy by dt is equal to 0. These are the two boundary conditions which we will apply to this equation to find out the values of A and B. Hence, what we have to do? Already we have found out the expression for y, but we do not know the expression for dy by dt. Let us now find out the expression for dy by dt, which can be obtained by differentiating this equation with respect to time. Let us now differentiate this equation for y and find dy by dt. We know that y is equal to a e to the power minus k plus root over of k square minus omega square into t, plus b e to the power minus k minus root over k square minus omega square whole into t. So, dy by dt will be how much? A minus k plus root over of k square minus omega square into t into e to the power minus k plus root over of k square minus omega square into t plus b whole into minus k minus root over of k square minus omega square, sorry no t is here, into e to the power minus k minus e to the power root over of k square minus omega square whole into t. Previously we have given equation 12 to this. So, this can be written as equation 13. Now, we have to apply the boundary conditions to this equation 12 and equation 13. What are the boundary conditions? What are the boundary conditions? Number 1, at t is equal to 0, y is equal to y0, and number 2, at t is equal to 0, dy by dt is equal to 0, because the boundary conditions are applied at the extreme positions where the displacement is maximum and the velocity is minimum and is equal to 0. So, what we have done? We have discussed damped harmonic oscillation. Also, we have derived the expression for the differential equation of damped vibrations, and we have found the solution of damped harmonic oscillation as y is equal to this much, and differentiating y we have found this, and the boundary conditions at the extreme points are these two boundary conditions at t is equal to 0, y is equal to 0 and dy by dt is equal to 0. Okay. Thank you very much.